So like I said, today's lecture is going to walk you through the mathematics behind spectroscopy. So we're going to start with a little bit of background. We're going to talk about two important vocabulary words or concepts that you must have in your head. The difference between levels and lines. Remember the first spectroscopic experiment in the spectrometer invented by Boltzmann was shining the light of a slit, a vertical slit, and a little gas discharge tube onto some photographic plates. And because it was dispersed, you've got specific lines where there was a spectroscopic transition. And so when we started putting those in a graph instead of a photographic plate, we would see these bumps, these peaks. We call them peaks. But we kept the old term lines. So the lines on those photographic plates, nowadays we call those peaks. So lines and peaks are the same thing. And these lines or peaks are the differences in the energies. So the energy levels, that's what comes out of the quantum mechanical calculation. You solve the Schrodinger equation, which we'll talk about today, and you get the energy levels for a system. So light is absorbed or emitted, causing a jump up or down in the energy levels. And the difference between those energy levels are the lines. So that's a spectral line up here, where you have a difference between E3 and E2. So if an atom or a molecule drops from that level down, it spits out a photon of light that has this wavelength. And that energy is the difference between those energy levels. So lines are energy differences between two levels. This is another spectral line. This is dropping from E2 down to E1. And you see that the wavelength is a little bit different. The energy is different. You get a different spectral line. That peak's going to show up in a different place in a spectrum. If you jump from E3 all the way down to E1, you have a large energy difference, and so you have a very short wavelength. So these are three different spectral lines that come from the differences of three different energy levels. And so way up here, notice these energy levels are close together. And so that gives you a low energy difference. That would be a low frequency or a long wavelength. Those three things go together. Low energy difference, low frequency, long wavelength. Because wavelength and frequency are inversely proportional. And then down here, this bottom one, this short wavelength, high frequency, and high energy difference. So this is the largest energy difference, so it has the highest frequency, and it has the shortest wavelength. So in your mind, this would be a three-level system, three energy level system. And these are the three different transitions that you can get from this. And you should be able to understand the difference between levels and spectral lines. Levels are the three energy levels, and the spectral lines are the differences between those. So let's go back to the data, that blackbody radiation. So this is the blackbody radiation, three different temperatures. You see the maximum wavelength is longer for the lower temperature. As you get higher temperature, that maximum wavelength gets shorter and shorter. You see it starts to move into the visible around 3000 Kelvin. You start to see some red. So your stove burner is getting up close to 3000 Kelvin when it's emitting red light. Okay. If you were to crank more amps through that, it might turn white eventually, where it's emitting all of the wavelengths of light and getting up close to 5000 Kelvin. But the metal might start to melt close to that. So you can just put enough amperage through it to melt metal. We had a stock pot melt on our stove. It was aluminum, so it had a lower melting point. And we came in, the water had boiled away, we were eating outside, and we picked the stock pot up, and the bottom of the pot stayed on the burner. Yeah, it was bad. Some of it drifted off onto the linoleum and burned some linoleum. So really dangerous. If that had fallen on your shoe, it would have burned right through the shoe and right through your foot until it cooled down. So anyway, we have blackbody radiation and the Planck distribution, and then we have that Rayleigh-Jeans law. This is the classical theory at 5,000 Kelvin. Of course, it goes to infinity. And so that was the UV catastrophe. So this is the data. And this is a pretty complex system, right? This is atoms in a hot object, and they're vibrating in 3 dimensions, and they're emitting photons of light and all different kinds of wavelengths. And that's going to be a difficult system to study. So maybe we could simulate this. Maybe we could get a simple one-dimensional system to simulate this spectrum, this experimental spectrum. And so that's what we have here. We have in this dashed line the Planck distribution, which would represent the blackbody radiator, okay, the energy coming out of a black body. And then this solid line here with a few bumps here, but notice how it matches pretty well the Planck distribution. And this is the simulated spectrum of just a single electron in a 7 angstrom box at 200,000 Kelvin. Now, why so hot? Well, because to get a single electron to behave like a blackbody radiator, you have a different temperature. Okay, you need to really excite it. And so don't get hung up on the temperature or the size of the box. I mean, this is 7 angstroms. That would be kind of like putting an electron on a 7 angstrom wire, very tiny little wire. And it doesn't have enough energy to leave. So it's stuck on a wire. That's kind of what we mean by a particle in a box. A particle is confined to some space, and we have a one-dimensional box, so you can think of it as a line. And so that electron is stuck on a line, 7 angstroms, and it's at a really hot temperature. And we can get it to look just like the blackbody radiator. So now this is an important principle in CHEM and in science in general. If you can simulate it, you can understand it. And so we've simulated the black body using a one-dimensional model. And now we can pull the thread and look at every equation that builds up this spectrum. So we can go through, and we've simulated it. Now let's pull the thread. Let's go from the data backwards down to the wave function. Instead of starting with the wave function, which you really don't have much familiarity with, let's start with the spectrum of a hot object, which is your stove burner. Okay? Let's simulate that burning hot stove element with an electron on a wire, and let's see what pieces went into that simulation. So now we'll just sort of go backwards all the way down, dig down deep into the wave function. So these are all of the different kinds of spectral transitions that we have. And what we're modeling is emission. So over here we have absorption. It may be a little small for you to see, but like I said, this is all in that chapter. If you come in, a photon of light hits a particle sitting in a lower energy state, and that particle absorbs the energy and goes up and is now at an excited energy state. So that's absorption. Over here, let's skip that one for a second. Over here, a particle is in this excited state, and it spits out a photon and drops down at the same time. So that's emission. So whenever you have a particle in an excited system, it can spit out a photon and drop down. And that's called spontaneous emission. We really can't predict when that will happen. We can do a statistical measurement and say it is this likely to happen, but we can't look at a particular particle and tell when that particle is going to spit out a photon. That is still a mystery in quantum mechanics. We have no idea when a particular particle is going to just spit out a photon and drop. Okay. So that's emission. Now this one, that's spontaneous emission. This one is stimulated emission. Here we have a particle and a photon that happens to match this energy difference. It has the right energy, the right wavelength, right frequency, comes and bumps that particle and causes it to spit out a photon that's in phase with the first photon, and it drops down. So that's stimulated emission. And you've probably heard of stimulated emission. It's the S and E letters for laser. So light amplification by stimulated emission of radiation is what's going on here. So we put these excited particles in a cavity, and we send a photon through at the right frequency, and that photon gets amplified as all those particles drop down. There's stimulated emission and light amplification. And so that's what makes this so bright. So we have an excited system in here, and we put electricity through a diode, and that diode emits a red photon, and it goes through and causes all of these other excited particles to drop down at the same exact frequency and builds up a very bright light. This is very, very bright compared to the amount of energy I'm putting into it.
Is it because they're in phase?
That's why it's so bright. They're all in phase. So they drop down it's just in concert. And they just keep building up that wave. And it's much, much brighter compared to the amount of energy you put in. If you put that same amount of energy into just a hot wire, like an incandescent bulb, you probably wouldn't even see it. You couldn't see that it was coming on. Then these others we'll talk more about. They are scattering techniques. So a photon notice a photon comes in and a photon goes out. And this would be Rayleigh scattering, and these are the Raman effect, inelastic scattering. A photon comes in and then goes out with a different wavelength. And so we'll talk about those much, much more later. But for now, let's focus on emission, because that's what's going on with the blackbody radiation. We're getting emitted light out. And so let's just focus on the emission and absorption. I mean, they're the same probability. One goes up, the other goes down. So I've got a lot of these equations written as absorption, but they also correspond to emission. So what goes into making a peak the height that it is, right? What makes this little peak here small, that one medium, and this one really tall? So what goes into that absorption intensity or that emission intensity? It's pretty simple. Absorption A is equal to the sum of big. Okay, go big or go home. All right, so BIG. Let's talk about each of those three pieces. Okay, now this is absorption as a function of wavelength, and so as we go through the spectrum, we sit at a wavelength and we add up at that wavelength all the pieces that add up at that wavelength. Then we move to a different wavelength and add up all those pieces. So we're doing a summation over the quantum numbers and over the wavelength. So right here, this B piece is Boltzmann's distribution. And remember I said that he had a huge contribution and really, I think, is the father of quantum mechanics. It's the thermal population of energy levels. For an atom to absorb light from a given energy level, it has to be there. It has to be at that energy. Or for one to emit light, it has to be at that higher energy. So Boltzmann's distribution tells us the relative populations, the probability of being in an excited state or in a ground state. And so if you heat the system up, you're going to have more probability of atoms being in the excited state.
So it's not like the population of electrons, it's just the probability of the level.
So if you think about, since we're familiar with, had a couple years of chemistry, we're familiar with atoms, right? And the Aufbau filling principle, S, 1s, 2s, 2p. Okay, so if we pick something like, like hydrogen, okay? It's just 1s1. There's an electron in the 1s orbital, okay? This would tell us the probability at a given temperature for that single electron to be in the 2p orbital. We say the electron configuration for hydrogen is 1s1, and that's the ground state, okay? If you raise its temperature high enough, that electron could be in the 2s or the 2p. And Boltzmann's distribution would tell us what the probabilities would be at a given temperature. So if we really heat up a hydrogen atom, most of them would still be in the 1s orbital, 1s1, but maybe 50%, well, that's too high. See, 10% would be in the 2s, and maybe 0.5% would be in the 2p. And that would be the thermal population of the electrons in a hydrogen atom. So you had a mole of hydrogen atoms, only 10% of them would be excited, and that would be the Boltzmann distribution. And so then you could get emission out of a hydrogen atom at a higher temperature. Whereas if you just had all ground state hydrogens, everything's in the 1s, you're not going to get emission because they can't go down to any lower levels. 1s is as low as it goes. So the Boltzmann distribution gives us that thermal equilibrium and tells us where the system is in terms of its excitation. Okay. Now I is the transition. Think of integral, okay? Integral. And that's an integral. We will see what that is in the next slide or two, okay? So this transition dipole moment is an integral, and that gives us the intensity of the peak. And it has to do with the overlap of the wave functions. So if the wave functions don't really overlap, even though you have the thermal population, you have the light coming in or the light going out, it could have a transition. The probability from this integral is really low or 0 if it's a forbidden transition. Or it could be high, or it could be somewhere in between. And then G, you can just think of Gaussian line shape. Not all your spectra have Gaussian line shapes, but the ones that we deal with in this class will be a Gaussian line shape. There are other line shapes, and you can read about those in that chapter. There's Lorentzian, there's log normal, a Voigt. So there's other ways, other shapes to the peaks. And so this is, we'll see next, how all of these pieces fit together. So this is what makes up a peak in a spectrum, are these 3 different calculations. And so here I've broken it apart into its various pieces. So this A, this absorption intensity, is the total curve here that's being shown. So this is that total piece. And then this Boltzmann population is this dashed line right here. And notice how it goes down to 0. This is wavelength being plotted down at the bottom. And so remember, these different transition are spectral lines. These are differences in energy levels. And so this one right here is going to be from the ground state to the first available excited state. Okay? It's the longest wavelength, and so it's the shortest distance. Ground state to that first excited state. What about one that's way over here? That's such a very short wavelength. That means it's a really big jump. Okay? And it's just not very probable that you're going to jump that far. Also, these are some other excitations where you might be from the second state and jumping up, or the third state and jumping up. Eventually, you don't have any molecules that are excited that high, and the Boltzmann distribution tells us that. So the Boltzmann distribution goes to 0 up here at the top. And so that's causing all of these peaks to go down to 0. Then this I piece is right here. This stick is the integral result from n to n prime. Okay, so that I is that stick. And then what gives the peak its shape is the G. So the G gives it this Gaussian shape. I don't know if you've ever taken statistics, but that's a Gaussian curve. That's a normal distribution. Now, how does it fit into here? Well, normal distribution is just random fluctuations. And molecules and their energy levels have some random fluctuation to them. And so you get that same randomness showing up at every absorption. Now, why does the absorption peak here not go down like these peaks do? It goes up. Well, look, this whole thing is a summation over wavelength. And so sitting at this wavelength right here, I get the summation of every one of these curves. And they all add up. And so right there at this maximum, I'm getting the summed intensity of all of these curves on top of each other. So at that wavelength, I have a lot of ways light could be absorbed, or if I'm doing emission, a lot of ways light could be emitted. It's going from this energy level to that one, or maybe this one to that one, or this one to that one. And those differences are all very much the same, and so they add up. Light, if this is absorption, very little light gets through because it has so many options of how it can be absorbed. Or if it's being emitted at that wavelength, it's very bright because so many different differences in energy level can be spitting out that same wavelength of light. Any questions on this? This is a very important slide for you to understand. So this is a spectrum, either an absorption spectrum or an emission spectrum. You'll get the same science behind it.
So I understand how the different drops will make new lines, but what were you saying that some, like the same levels will make the same line? Is that what you were saying?
Each one of these peaks corresponds to a specific difference. Like this one here is from 1 to 2. And so that's from energy level 1 to energy level 2, and it always shows up wherever that difference is, that's the wavelength. You convert to wavelength, and that's where that is. So that peak is this one. And when we go through our lab and we assign quantum numbers to the various peaks, we're assigning the spectrum. So you will actually do that. This class will teach you how to take a spectrum and tell me and yourself specifically what quantum numbers are involved with every peak. Okay. Now sometimes you can't resolve them. And so when they get over here and they start to overlap, you're not able to assign a particular quantum numbers to those because the peaks are overlapped and you just can't see them. You can't see the individual transitions. They're all overlapped. And so in this spectrum here, if I were to assign this, I would say, well, I know this is the longest wavelength, so that's the very first transition. So that's going to be 1 to 2, and this will be 2 to 3, but then I can't resolve any of the ones under this peak. And so I couldn't put a quantum number assignment to this because there's so many different options of quantum numbers. And so I would just say not resolved on that one. But I could assign 2 peaks in this and say the first one is the 1 to 2, the next one is the 2 to 3, and then the rest are not resolved. They're just overlapped. Okay. That help, kind of? Okay.
So those all count as like one, but we're not even.
Yeah, but it's not a single transition. It's got actually it's like 120 peaks underneath that curve. Yeah. Which you wouldn't expect. If you were looking at a UV spectrum or UV vis, this is a lot within the visible region. This is what you see in a UV vis experiment. You see these big broad peaks and you say, wow, I've got 3 transitions. Well, no, you've probably got 300 under those peaks. Yeah. Whoa. Now, as we go through the math, we talked about Schrodinger and then we talked about Dirac. And Dirac used a shorthand that's very convenient to use. And I'd like to teach that to you and use it throughout the course. And so this is, again, a very important slide. If you're kind of drifting off, wake up and look at this. Because whenever I write with these angle brackets, this is what I'm going to write with these angle brackets here. And then these vertical lines. And this means integral over all space, and it's these functions times each other. So you see on the left we have a wave function times x times another wave function in these angle brackets, and that's Dirac notation. And it's just a shorthand for writing the integral over all space of these 3 functions times each other. And this is a new slide. It's not in the notes if you've got the notes printed off. I just was looking at the notes and was like, oh, I didn't actually explicitly say what Dirac notation was. And so I needed to add that this morning. Now, all space in our one-dimensional case is just dx. But if we were doing a hydrogen atom and we were in spherical polar coordinates, it would be r, theta, and phi. So the angle around from the x-axis and then the angle down from z. Like on the planet, r would be from the center of the planet out to the surface, and then latitude and longitude. So we deal in spherical polars. We don't talk too much about r, except that's altitude, and we put relative to sea level. Okay, so that's r, and then latitude and longitude are theta and phi. So that's spherical polar coordinates, and you would integrate overall space. So you would integrate the radius, and then theta and phi. If you were dealing in a Cartesian system, you'd have a triple integral of integration over x, y, and z. But we're just going to stick to one dimension and do this particle in a box where we're integrating only over x. And so today's integrals that you do in lab will just be by dx. Yeah. Almost done writing. Did you at least get the equation down? Hopefully. Okay, so I'm going to move on. Now, let's talk about that I piece. So this piece right here in the transition peak, so each peak has a different I. And these are the transition moment integrals. And notice here, it's got x in it. And then these things here are the wave functions. So this is the first time we've seen the wave function. We've got a peak. The peak has a Boltzmann piece, a transition probability piece, that's the I, and a line shape piece. And then that transition probability I has the wave function. And so we'll get to what the wave function is in a second. We're just kind of going backwards, drilling down to find out what that wave function is that simulates our spectrum. And so what this tells us is intensity, that's what I is, intensity of the peak, is proportional to, that's what this little, looks like an alpha, is proportional to the transition moment integral squared. So if I can calculate that transition moment integral and I get 0, I know there's no intensity there. We call that a forbidden transition. And if I calculate that transition moment integral and I get a big result, then that's a strong peak. If I calculate the transition integral and I get a small number, that's a weak peak. So you have some peaks that are small, some that are really big, and some that have 0 intensity. No, yes?
What's the difference between the x in the bars and the x in the parentheses?
The x in the parentheses is the dimension x.
Okay.
And the x inside the bars is also the dimension x. So there's really no difference. Notice the x in parentheses, though, that's the wave function as a function of x.
Okay.
So psi is a wave function, and it's a function of x.
Mm-hmm.
So that's a pretty good question, just to clarify. All right. So that psi of x is the wave function, which is a function of x, and then the x's inside the bars is the x-axis. Now, why are we using the x-axis? We'll talk about it in a second. Yes?
So it's sort of like f of x, but you're saying
Psi of x. Yeah, excellent. And that little subscript n is the quantum number. And we'll see that, so we're pulling the thread. It's kind of a different way to go through it. We're just pulling, we see this equation, we're like, great, now what's psi n of x? We'll see that come out. But I want to show you where it comes from. So we've got this transition intensity, this peak, and it's got 3 parts: the Boltzmann part, the intensity part, which is here, and the line shape part. And so then that intensity part has the wave function in it. The scattering one we'll talk about later. Then we have the Boltzmann piece. This is the Boltzmann distribution. It has the energy levels in it. And it has temperature. So that's pretty cool. We have the energy of the system, like a hydrogen atom, or in our case, an electron on a wire. And then it's temperature dependent. So this will give us a spectrum that's temperature dependent. This G of N is degeneracy. So you've already experienced this degeneracy term. Think about the s orbitals. It's just one s or two s, but the 2p, there's three of them. So the 2p orbitals, it's a degeneracy of 3. What about the d orbitals? Degeneracy of 5. And the f orbitals? 7. Okay, so you've already experienced degeneracy. It's different wave functions that have the same energy. Okay, and it's how many wave functions have the same energy is your degeneracy. So in the p orbitals, px, py, pz, those are 3 different wave functions, but they have the same energy. And so for Boltzmann, Boltzmann's a statistical calculation. And so if I'm trying to figure out where I can put my electrons, I have 3 options for the p orbitals. So I want to multiply that probability by 3. And so that's where the degeneracy comes in. Okay. And then we get to the energies. Because the Boltzmann factor had energy in there, how do we solve for the energies? That's where Schrodinger's equation comes in. And so this is the Schrodinger equation right here. So the energies of the system are solved for by Schrodinger's equation. So and the thing that gives the energies is the Hamiltonian. And again, the wave functions are operated on by the Hamiltonian. You take the integration of over all space, and you get the energy levels for that system. So that Hamiltonian is shown down here. And you see it has 2 pieces to it. The V is potential energy. And then this first piece is the kinetic energy. If possible, we like to set the potential energy to 0 so we can get rid of it. And in our particle in a box, we say when the electron's inside the box, it has 0 potential energy. It's not uphill from anything. It's in the ground state. It's relaxed. But if it wants to get off the wire, it has to have an infinite potential energy. So it can't do that. So we have potential energy set to 0, and then we solve for the kinetic energy. And notice it's the second derivative with respect to x. And so what does that tell us about x? The first derivative is slope. You remember that? First derivative is slope. Do you remember what the second derivative is called? Sorry? So yeah, it tells you how it's changing, how the slope is changing. So it's kind of the slope of the slope. But there's another word for that. It's called curvature. So if you have a wave function, the curvature of that wave function is proportional to the kinetic energy. That's a very good concept for you to have in your head. If you have a wave function that's curving a lot, higher energy than a wave function that's not curving very much. So a wave function can't curve a lot without going through 0 a bunch. So wave functions that have more nodes have higher energy. And it's related to that second derivative. If it's curving a lot and has lots of nodes, it's a higher energy than if it's not curving very much and has no nodes. So we've seen the wave function in the intensity equation, and we've seen the wave function in the energy equation. And so it's everywhere in spectroscopy. So if you understand the wave function of a system, you understand its spectroscopy. you understand where the energy levels are and their differences, and you understand how intense the peak is going to be. And so this is the wave function for the particle in a box. So it has a normalization constant here. We'll discuss next time what that does for us. Or you'll learn about it in the lab today too. It's a sine function. What it essentially does is it converts x and divides it by L. So the length of the box goes from x equals 0 to L. And then it's converting it to radians by using this pi. And then n is a frequency factor or quantum number. If I raise n by integers, I just create more and more lobes and nodes inside this box. So let's look at the wave function plotted. Here's our one-dimensional box. The x-axis is our box. It's a box because at the edges of the box, the potential energy goes to infinity. And inside the box, the potential energy is 0. So for an electron to leave the box, it has to have an infinite energy. That's convenient. It's not going to have an infinite energy. Okay? And so then this is that wave function plotted. When n equals 1, this is what you have. Just half of a lobe, or a half of a wave of that sine wave. When n equals 2, then you get the full sine wave. When n equals 3, you get 1.5 pieces of the sine wave. You see the nodes, you see the lobes, and over time this is oscillating. So this is a wave function, so it's waving back and forth. Yeah. And so this right here is the wave function that generated that spectrum that looks so much like a blackbody radiator. And you will now start in lab with the wave function, and you will normalize it. Okay, let's try to go back. You will normalize it using this integral here, okay, and show that the wave function is normalized. You'll solve for the energies using the Schrodinger equation, and then you'll go to this and you'll solve for the transition moment integral. And so those are the three main integrations that you'll do. And this transition moment integral, notice, has two different quantum numbers. You've got an n and an n prime. And your groups will all have different n's and n primes. Okay, so you can talk to each other to do the integrals, but you'll have different results. And so you'll be able to see, some of you, when you do that integration, will get 0, which means that transition is not allowed. And others will get non-zero results, which means it is allowed. Some will get big numbers, which means it's a strong peak. Others will get small numbers, which means it's a weak transition. And if we put all of our results together, later on in the week, we'll be able to get what we call the selection rules for this particular system, meaning which peaks are allowed and which peaks are forbidden. And that's a main part of the course, is understanding the selection rules in a given system. So that's I know we've covered a lot. We didn't get to do the Kahoot midway, but checking the time, we really didn't have time for it. Excellent. See you next time.